All right, this is the Unit 4 review. First two questions come from section 5.1. This is called finding a particular solution. What that means is we use indefinite integration to find the antiderivative and then find the particular value of c using this initial condition. So let's first start by using indefinite integration. You need to find the antiderivative of the square root of x. So essentially we need to find the antiderivative of x to the 1/2 dx. So using rules of integration, we add 1 to the exponent and then divide by it. So if you add 1 to 1/2, you're going to get 3/2. And then if you divide by 3/2, that's the same as multiplying by 2/3. And then we add c. So this is our antiderivative f of x. Now we're given an x value here of 9. So this is what x equals. And this value, we know that f of x equals 4. So if we plug those values in now, a 9 for x, and then a 4 for f of x, that's going to allow us to find that missing value of c. So starting here, 9 to the 3/2, well, that's the square root of 9, which is 3, and then 3 cubed is 27. So this is 2/3 times 27 plus c equals 4. 2/3 of 27 is 18. And if you subtract 18 on both sides, you get a value that c equals -14. So then we know that f of x equals 2/3 x to the 3/2 minus 14. So we're going to do a similar thing here on question 2. We need to find the antiderivative of 4x plus 2. So it's going to be 4x squared over 2 plus 2x. So we know that f of x equals 2x squared plus 2x plus c. Using the same thing, we know that x equals -2 and f of x equals 1. So we can make the substitutions. -2 squared is 4, 4 times 2 is 8, and then 8 minus 4 is 4, so we have 4 plus c. So c equals -3. So the particular solution is 2x squared plus 2x minus 3. Now 5.2 is when we learned about substitution, use substitution, in particular with the general power rule. So if you remember, the general power rule is u to the power of n du. The antiderivative is u to the n plus 1 divided by n plus 1 plus c. That's the general power rule. So what we need to do is figure out an inside function for u for each of these. So I'm looking at right here an inside function. So we could say that u is equal to x cubed minus 2. Then if we take the derivative, that's 3x squared dx. And we've got the 3x squared and the dx. So that antiderivative can turn into instead of x cubed minus 2 to the third power, it's u to the third du. And the antiderivative of u to the third is u to the fourth over 4. So now we can undo the substitution for u and call it x to the third minus 2 to the fourth power all over 4 plus c. Now for number 4, I see an inside function here, and then we can also change the cube root. We can change that into a power of 1/3. So I'm going to say that u is the inside function 5x to the third minus 1, so then du is 15x squared dx. So we're supposed to have a 15x squared dx. I've got the x squared and the dx, but I've got a 45 right there. Well, 45 is 15 times 3. So if I split the 45 and left a 15 and then pull the 3 out of it, then I'd have the 15x squared. So I can call this 3, and then u to the 1/3 du. And this 3 is just a coefficient, so it's going to stay a 3. The antiderivative of, let's get back there, the antiderivative of u to the 1/3 is u to the 4/3, and then we either divide by 4/3 or multiply by 3/4. So this 3 times 3 there, that's going to become a 27. So 27, what am I talking about? That's 9. I'm thinking 3 to the third power. 3 times 3 is 9. Time to wake up. All right, 3 times 3 is 9, and then we can undo the u substitution, which is 5x to the third minus 1. That's raised to the 4/3 power divided by 4 plus c. .3, we learned 2 other rules using u substitution. Exponential rule was e to the u du is e to the u. And then the logarithm rule was the antiderivative of du over u is the natural log of u. So those are the 2 rules that we learned in 5.3. So it looks like number 5 is going to be following the logarithm rule because it's in the form of a fraction, so that means the denominator we could let equal u. Du would be 6x dx. So we've got the x dx in the numerator, because remember we're supposed to try to have a du in the numerator. We got an 18 and it's supposed to be a 6. Well, 18 is 6 times 3, so I could leave the 6 there and pull a 3 out. That'll give me the 18 and then the 6 dx like I need. So I can call this the antiderivative of du over u, because du is 6x dx and u is 3x squared plus 4. Well, the antiderivative of du over u is natural log of u, so this is 3 times the natural log of absolute value of u, and then undo your u substitution. So number 6, we have e raised to a power, so we could try to let that power be our u. So u is equal to x to the third plus 4. So du would be 3x squared dx. We've got the x squared dx, but it's supposed to be 3x squared, not negative 6. But negative 6 could be 3 times negative 2, so I left the 3 there and put the negative 2 out there. That would be negative 6, and it would also be the 3x squared that I need. So I can change this into e to the u du. And the antiderivative of e to the u is e to the u. And then you can undo the u substitution and leave it like that. Okay. Number 7's probably going to be a lot like number 5. We can try du over u. So u would be the denominator, du would be the derivative of that, which is going to be 25x to the 4th. So I've got the x to the 4th dx, but that negative 75 should be a positive 25. So instead of a negative 75, I could say this 25 with a negative 3 out front. So then this changes into negative 3 times the antiderivative of du over u, which is the antiderivative of du over u is natural log of u. And then you can undo the u substitution for the answer. Okay, we have e to a power, so we can try the e to the u, the exponential rule, which means the power would be our u so we've got the x and the dx, but that 6x is supposed to be a 2x. So the 6 I can change into a 2 multiplied by a 3. So now we've got e to the u du. Okay, those all have been examples of indefinite integration. 5.4 we learned about the fundamental theorem of calculus. Definite integration helped us find the area under a curve. Uses the same ways of integration, so substitution rule up until this point. And we just apply the fundamental theorem of calculus after we find the antiderivative. So what we're going to do on number 9 is rewrite the integral. And I'm going to bring the expression in the denominator up to the numerator. This will be an example of the general power rule. We have u to the power of n. So that means u is going to be the inside function, x minus 2 du is 1 dx. So that 5 just needs to be moved out in front. Now I'm going to drop the limits of integration until we find the antiderivative. So this is u to the power of negative 2 du. The antiderivative of u to the negative 2 is u to negative 1 divided by negative 1. So that's the same as negative 5 over u, which is negative 5 over x minus 2. Now we're going to use the fundamental theorem of calculus. With our bounds of integration, we always start with the upper bound. So that's negative 5 over 5 minus 2, and then we subtract the antiderivative evaluated at the lower bound. That would be negative 5 over 3 minus 2. So this is negative 5 thirds plus 5. 5 is the same as 15 thirds, so negative 5 thirds plus 15 thirds is 10 thirds. So for number 10, we're going to try the exponential rule because we have e to a power. So we could say that u is equal to that power. So then du would be the derivative, which is 2 dx. We've got the 2 and the dx. All that needs to change is that minus sign, just going to move out front. So again, I'm going to drop the bounds of integration just so I don't have to write them. I'm just going to find the antiderivative. So we've got that negative, and then the 2e to the 2x plus 6 can become e to the u du. The antiderivative is e to the... So that's negative e to the 2x plus 6. We're going to evaluate that from negative 3, negative 6. So we start with the upper limit. So it's going to be the opposite of e to the negative 6 plus 6, that's 0, minus the opposite of e to the negative 12 plus 6, that's negative 6. Now here, e to the 0, that's just 1, so we have negative 1 plus e to negative 6, which is negative 1 plus 1 over e to the 6. All right, section 5.5 is an extension really of 5.4. We're still using fundamental theorem of calculus to find the area, but this time the area is bounded by two graphs. So the first thing we need to find on number 11 are the intersection points of the graph. Where does this first one, I'm going to call this y1, where does it intersect with y2? So a quick way of finding that is to set the two functions equal to each other. And then solve for x. So I'm going to get one side equal to 0. And you can factor out an x. And then continue to factor. So we have x equals 0, x equals negative 2, and x equals 1. So this is a little unusual that we have 3 points of intersection. So what's happening here? We don't need to graph it, but I'll do my best. It's a cubic, so you know I might look. Well, let's try that again. It might look something like that, and then we have an upside down parabola, negative x squared. So you know it could look something like that, an upside down parabola. So what we actually have are two bounded regions. And this graph isn't exact, I'm just drawing examples. So we have this region here and this region here. That's why we have 1, 2, 3, spots where these graphs intersect. So, for example, -2 to 0, and then 0 to +1. So after you find where the graphs intersect, you need to figure out which one is the upper function, which one is the lower function. I'm going to use my example here, and again, remember, this may not be what these graphs actually look like. But between here and here, we've got the x to the third function that's on top, and then the x squared function is underneath, but then it switches at this intersection point to this intersection point. Now the x squared is up top, and the x to the third function is underneath. So we need to figure out which function is the top function and which function is the bottom function in between each of those points of intersection. So I'm going to start between between -2 and 0. So I'm going to try to figure that one out. So between x equals -2 and x equals 0, what you need to do is choose a number between those. So between x equals -2 and x equals 0 would be something like x equals -1, and you plug that into both functions. So y1 at x equals -1. So if I plug in x equals -1 into y1 here, I'm going to get -1 cubed, that's -1. And then -4 times -1 is +4, so that's going to give me a 3. y2 now, we already did y1. y2 at x equals -1. So now we go up to y2. So if I plug in -1 and square it, that's going to be 1, but then you multiply it by that negative, so it's -1. And then -2 times -1, that's +2. So that equals 1. So this one is the upper, and that one is the lower. Now, between 0 and 1, we don't have many options there. We have +1/2. So y1 at x equals 1/2 is, okay, so 1/2 raised to the third power is 1/8, and then -4 times 1/2, so that's -2. 1/8 minus 2. Well, that becomes 1/8 minus 16/8. So that's -15/8. And then y2 at x equals 1/2. So if we go up here, 1/2 squared is 1/4. So this is -1/4 minus half of 2 is 1. So -1/4 minus 4/4 is -5/4. Five-fourths is -10/8. So this one now is smaller. -15/8 is smaller, more negative than -5/4. So this is now the lower, and that one's the upper. So we're going to have to split this up into two problems. This one is going to be the integral from -2 to 0 of the upper function, which is y1 minus, and then you subtract the lower function. This one here is going to have to be the integral between 0 and 1 of the upper function, which is y2 minus y1. And then we have to add these two results. So this turns in to -2 to 0. y1 is x cubed minus 4x, and then we subtract -x squared minus 2x. So that's x cubed. That's going to be plus x squared, and then minus 2x. And we can just find the antiderivative of each term individually. So that's going to be x to the 4th over 4 plus x cubed over 3 minus x squared. And we're going to evaluate that from -2 to 0. At the upper limit, that's just going to be 0. And then at the lower one, that's going to be -2 to the 4th power. That's 16 fourths. -2 to the 3rd power is -8 thirds. And then -2 squared is 4. So that's 0 minus 4 plus 8 thirds plus 4. The -4 and the +4 would cancel. So we get 8 thirds. Now this one is y2 minus y1, so that's -x squared. What was y2? Minus 2x. And then we subtract x cubed minus 4x. So that's -x cubed minus x squared plus 2x. The antiderivative is going to be -x to the 4th over 4 minus x cubed over 3 plus x squared. And then the fundamental theorem of calculus is from 0 to 1. So at the upper limit of 1, we're going to get 1 to the 4th power is 1, but then negative, so -1/4 minus 1/3 plus 1, and then subtract at the lower limit, which is 0. So this is -3/12 minus 4/12 plus 12/12. So that's -7/12 plus 12/12. That's 5/12. So now we add those two results, 8 thirds plus 5/12. 8 thirds we can turn into 12ths. That's 32 12ths plus 5 12ths is 37 12ths. And again, there's no reason you shouldn't be using a calculator for all of this. Turn it into decimals, whatever you need to do. I'm doing this by hand, so I don't have a calculator. Okay, number 12 is an application of what we just did, finding the area bounded by two graphs. If we were to look at graphs of supply and demand, we've got our demand function here, and we've got our supply function here. So demand, supply. right here is the point of equilibrium. So we have excuse me, we have an x value there, and the vertical axis is price, so we have a price. Consumer and producer surplus would be the areas here and the area there. So those are the areas we're going to try to find. Let's start with consumer surplus. That's this area right here. That would be that top triangle. So what we need to first find is that point of equilibrium where supply and demand meet. So set the two equations equal to each other. If we want to get all the x's on one side and just solve this equation. So just solving this equation, we're going to have 150 equals 1.5x. Dividing both sides by 1.5. It gives us 100. So the x value, or number of units of equilibrium, is x equals 100. Now we need to find a price. We can plug 100 into any of the supply or demand functions there to get the p-value. So if we plug in 100 into there, for example, we're going to get 130. If you add 50, that's 180. So price equals 180. Now consumer surplus, if we're going to find the area underneath demand and above that price point of $180, then we're going to be finding an integral from 0 to 100. The upper function is demand, which is 200 minus 0.2x, and then we subtract the lower function, which is 180. So this is 200 minus 180 is 20, so this is 20 minus 0.2x. So the antiderivative is 20x minus 0.2 x squared over 2. And then 0.2 divided by 2 is 0.1. So we have 20x minus 0.1 x squared. Now we apply the fundamental theorem of calculus. So if we have 20 and we plug 100 in for that x, that's 2,000. And then if we have 100 squared multiplied by 0.1, that's 1,000. So the consumer surplus is $1,000. Now, producer surplus would be the area below this price point of $180 and above the supply function here. So we're still going to find the definite integral from 0 to 100, but now the upper function is the price of 180, and now we subtract supply. So that's 180 minus 50 is 130 minus 1.3. So the antiderivative there is 130x minus 1.3x squared over 2. And then 1.3 divided by 2, 0.065, or 0.65. So this is 130 x minus 0.65 x squared. Applying the fundamental theorem of calculus, we're going to plug the 100 in first. That's going to be 130 times 100. It's 13,000. And then we're still plugging it in here, so we have 100 squared times 0.65. That's 6,500. Now this is just the antiderivative of the upper bound, 100. We still have to subtract the antiderivative at the lower bound, but since the lower bound is 0, we would just be subtracting 0. And it's the same thing here with this one. 2,000 minus 1,000 is the antiderivative of the upper bound, 100. If we were to plug 0 in for the x's, we're just subtracting 0. So now we've got 13,000 minus 6,500. That's 6,500. Now there is another way. If supply and demand are linear functions, then the consumer and producer surplus, let me zoom in here, are going to be right triangles. So we've got that right triangle for consumer surplus. If we wanted to figure out the area of a right triangle, we just need to use 1/2 base times height. So area here, let's get a different color, there we go. Area is 1/2 of the base, which is 100. Base going from here to here, times the height. Now this price point is 180, and the y-intercept of the demand function is 200, so that's a distance of 20. So we have 50 times 20, which is 1,000, which is what we got for the consumer surplus right here. Now the other one, producer surplus, it's the same thing, it's a right triangle, so we could find the area there as 1/2 base times the height. Now the y-intercept, let's see, is 50, and it goes all the way up to 180, so that's 130. So half of 100 is 50, and 50 times 130 is 6,500. So if your supply and demand functions are linear, then essentially you're just finding the area of right triangles. You're welcome to use the geometric formula for the area of a right triangle, 1/2 base times height. Okay, getting to chapter 6, section 6.1, we learned integration by parts. It was, if you can set up the integral as an expression u multiplied by another expression dv, then the integral would be u times v minus the integral of v times du. So the two things we need to try to find in each of these expressions is what's going to be u and what's going to be dv. The guidelines for this, if you recall, u needs to be something whose derivative du is a more simple form, and dv, if you choose an expression for dv, it needs to be something that's easy to integrate. So right here in number 13, we've got two expressions, x multiplied by e to the negative 3x. One of these has to be u, the other one has to be dv. Now I'm going to let x be my u expression, because when I take the derivative du, then the derivative is just 1 dx, and 1 is a more simple form of x. So that's a pretty good choice for u. Now dv then would have to be the remaining expression, e to the negative 3x dx. So I need to find v. V is the antiderivative, which means I have to integrate e to the negative 3x. In order to do this, I need to write this as e to the u. I need to do a little e to the u integration. So this is a separate u than this u right here. So if I let u equal negative 3x, then du is negative 3 dx. So I'm going to find the integral of this. I need to have a negative 3 in front, which means I need to have a negative 1/3 in front of that. So that's getting kind of messy to see there. Let me write this with a little more room. In order to find the antiderivative of e to the negative 3x, I need to have it be negative 3e to the negative 3x, so that I have my u and my du right there. But in order to multiply by this negative 3 right here, I need to multiply by a negative 1/3 out in front. So the antiderivative now of negative 3e to the negative 3x is e to the negative 3x. The 1/3 is just a coefficient. So there's what I've got. I've got my u, my du, my dv, my v. So the integral, the original problem that we had, can be rewritten as u times dv. So this, now we can use integration by parts. Integration by parts says we've got to write u times v minus the integral of v. Now v has a coefficient of negative 1/3, and I like to write those in front of the integral sign, times du. So we've got u times v minus the integral of v times du. This is just integration by parts formula that we're using here. There's not much we can do to simplify that expression. I'm just going to write it as negative 1/3 x e to negative 3x plus 1/3. And then we're back to this, the integral of the e to the negative 3x, but we already did that integral right there. And it turned out the integral was negative 1/3 e to the negative 3x. So multiplying those two coefficients, we're going to have 1/9 okay, similar, we've got to choose a u and a dv. Now we could say, all right, well, we could just let x equal u again, but that means dv would have to be natural log of 4x, and that's a pretty bad choice because there is no integral of natural log of 4x. That's not very easy to integrate. So we're going to rethink this here. I'm going to let u equal natural log of 4x, and dv is going to equal x dx. Now if we take the derivative of the natural log, it's 1 over 4x multiplied by the derivative of 4x, which is 4. So this equals 1 over x. v is the antiderivative of dv. The antiderivative of x is x squared over 2. So the original problem we had right here was u, and that was dv. So we had u times dv. So we can write this as, according to the integration by parts formula, u times v. So natural log of 4x multiplied by x squared over 2 minus the integral of v. Now v is x squared over 2. Over 2 is the same thing as being divided by 2, which is the same as multiplying by 1/2. So I'm going to move the 1/2 out front and just call this x squared. So there's v times du. Du is 1 over x dx. So with this expression here, again, there's not much that can be done with that. I'm just going to write the x squared over 2 in front of the natural log. So we've got x squared over 2 times the natural log of 4x minus 1/2 times the integral x squared times 1 over x is just x. And then the antiderivative here of x is x squared over 2. And we can multiply the 1/2 there with the other 1/2. We get a 1/4, or x squared over 4. Okay, first thing I'm going to do is look at this without a radical sign. So this is going to be x times x minus 3 to the 1/3. So we're going to do integration by parts. And the reason that, I know it specifically says use integration by parts. If the direction is just set to integrate, we wouldn't be able to use u substitution. Let me just illustrate this. If we want to do u substitution with the general power rule, then typically we let the inside function be our u. So we would have u equals x minus 3. That means du is 1 dx. So the problem is we have that extra x right there that we can't account for. So u substitution using the general power rule doesn't work on this problem. We've got to use integration by parts. So we need to choose a u and a dv. I'm going to let x equal u, and then dv is x minus 3 to the 1/3. Now the derivative of u, du, is just 1 dx. V is the antiderivative of dv. So if we integrate there, so v is the integral of dv, which is the integral of x minus 3 to the 1/3. We can integrate this just using the power rule. So x minus 3, we're going to add 1 to the exponent. So that's 4/3, and then we multiply that by the reciprocal 3/4. So setting this up, the integral, well, let's just go right into it. The integral of x times x minus 3 to the 1/3 dx is u times v. So we've got x times v, which is 3/4 x minus 3 to the 4/3 minus the integral of v. Now v has a coefficient, so I'm going to write it out front, times du. Now du is just 1 dx, or simply dx. This antiderivative we can simply use, again, the power rule. If we add 1 to 4/3, we're going to get 7/3. And then if we multiply by the reciprocal, that's 3/7. And multiplying these two coefficients, we're going to have 9/28 of x minus 3 to the 7/3. So 6.2, I know I called it 6.2, it was really 8.1 of the UVU edition. It was a appendix at the end of the book. These antiderivatives are going to be found using partial fraction decomposition. So if we break this rational expression into its partial fractions, we need to factor the denominator. So x squared minus 4x minus 5, that's going to be x minus 5 and x plus 1. So since there's two factors that form that denominator, that means there's going to be two partial fractions. And using the techniques that were shown in class, you can rewrite this expression, get rid of the denominator of each of these by multiplying the whole expression by the lowest common denominator. So that would leave this. Oh, anyway, skipped a step. I just don't have a lot of room. What happens there is you take this whole expression and you multiply it by the lowest common denominator. When it multiplies here, the denominators cancel. When it multiplies here, the x minus 5's cancel, so a is left multiplying x plus 1. When it multiplies here, the x plus 1's cancel, so b is multiplying the x minus 5. That's what's going on there. Now, to solve this equation, remember we're not solving for x, we're solving for a and b, so it doesn't matter what x equals. The problem is we have one equation with two unknowns, a and b. So in order to solve this, we need to get rid of either a or b. So the way that we do that is we let x equal a certain value. For example, if we let x equal -1, and I plug that in right there, not right there, plug it in right here, then -1 plus 1 is 0, and 0 times a is 0. So a disappears, letting us solve for b. So the equation would become b times -1 minus 5, that's -6. If we divide both sides by -6, we get b equals -2/3. Now, we need to figure out what a equals, so I want to cancel b. I'm going to let x equal 5 for this one. If x equals 5, the equation is 4 equals 6a. Divide by 6, you get a equals +2/3. So the original problem that we started with can be rewritten as the antiderivative of 2/3 over, what was it, x minus 5 plus -2/3 over x plus 1. This is the a right here, and this is the b that we just found. And then we could separate this into two different antiderivatives. So the antiderivative of 2/3 over x minus 5 dx plus the antiderivative of -2/3 over x plus 1 dx. Now the 2/3 here is just a coefficient, so I'm going to move that to the front. So 2/3 times the antiderivative of 1 over x minus 5. And the same thing, the -2/3 is just a coefficient, so I'm going to pull it out front and call it 1 over x plus 1. And then this is simply the natural log. The antiderivative of du over u is what that turns out to be, because if this is u, x minus 5, then du is just 1 dx, which we have right there. So what I'm saying is that this is really that, which is just the natural log of u, and that's the formula I'm going to use for these. So we have 2/3 times the natural log of x minus 5, and then we have minus 2/3, and this is the same thing. This is just the antiderivative, or the integral of du over u, which is the natural log of x plus 1. So we need to do a similar thing here. We need to factor the denominator. It's x minus 2, x minus 3. So we're going to have two partial fractions. And if we do the same thing, if we take this whole equation and multiply it by the lowest common denominator, we're going to end up with the equation 2x minus 3 rather. Equals a over x minus 3 plus b times x minus 2. Now, if I want to cancel that part of the equation, for example, so I could solve for b, I want x minus 3 to equal 0, so x has to equal 3. So if we let x equal 3 and I plug it in there, 2 times 3 is 6, 6 minus 3 is 3, so we get a 3. A cancels because 3 minus 3 is 0. Here, 3 minus 2 is 1, so 1 times b means b equals 3. Now, if I want to cancel b, I want to let x equal 2. If I plug in a 2 right there for x, 2 times 2 is 4, 4 minus 3 is 1. If I plug in a 2 right here, 2 minus 3 is negative 1. So a equals negative 1. So the original problem can be split up, this original problem here can be split up into its two separate partial fractions, a over x minus 2 plus b over x minus 3. And then we could write this as two separate antiderivatives. So the antiderivative of negative 1 over x minus 2 plus the antiderivative of 3 over x minus 3. Do the same thing I did in the other problem, just take these numerators and treat them as coefficients. And then we have same thing going on. That's the antiderivative of du over u, which is just the natural log okay. Same old, we just need to factor the denominator. Now we're going to have a 2x and an x. And in order to get the 12, let's see, we can have a 4 and a 3. So we've got 2x plus 3 and x plus 4. That means we have two partial fractions. If we solve that, or not solve it, but multiply each of those fractions by the lowest common denominator, then we end up with 5x equals a times x plus 4 plus b times 2x plus 3. Now, if I want to cancel a part of this. For example, I could let x equal -4, plugging it in there would give me -20. A disappears because -4 plus 4 is 0. Here, -4 plugged in for x gives us -8 plus 3. It's -5, so -5b, which means b equals 4. Now, if I want to cancel b, that means I need to figure out what makes 2x plus 3 equal to 0. So what makes 2x plus 3 equal to 0? Well, if you solve that equation, you're going to get -3 halves. So you're going to let x equal -3 halves for this one. If you plug that in here for x, you're going to get -15 over 2. If you plug it in here, you're going to get a times -3 halves plus 4. Now, that becomes -15 halves equals, let's see, 4 is 8 halves. 8 halves minus 3 halves is 5 halves. If you multiply both sides by, or divide by 5 halves, or you can multiply both sides by 2/5, that's going to be -15 over 5. So a equals -3. So the original problem is the antiderivative rather than one rational expression. It's the partial fractions a over 2x plus 3 plus b over x plus 4. And then we can separate that into two antiderivatives. Now I'm going to move that -3. This one is just going to be 4 times the natural log of x plus 4. Got to think a little more carefully about this one. We can still do du over u. But if that's my u, 2x plus 3, then du is 2. So really what I need to have is a 2 right there. Now I can multiply by a 2 as long as I divide by 2 right out there. So now that becomes -3 halves times the integral of du over u, which is natural log of u. And then plus c. Okay, 6.4 was improper integrals that uses limits. So what we need to do is change this into a limit problem as b approaches infinity. And then instead of going from the integral from 1 to infinity, it's now 1 to b. And then I'm going to switch this, instead of radical notation, I'm going to write it as x to the -1/4 dx. And that's just the general power rule. You're going to add 1 to it. So this is x to the 3/4. And then we need to multiply that by 4/3. And then the fundamental theorem of calculus is from 1 to b. So at the upper bound, we're going to have 4/3 times b to the 3/4, and then we subtract at the lower limit, which is 1. 1 to the 3/4 is 1, and then 1 times 4/3 is 4/3. So that antiderivative, remember, was in, we need to evaluate now the limit of that antiderivative, 4/3 b to the 3/4 minus 4/3. If we keep plugging in values for b that are getting bigger and bigger and bigger, then this whole expression just keeps getting bigger and bigger and bigger. And we talked about this in class. This is behavior. The two words we're looking for here is converges or diverges. Converges means that the value as b gets larger towards positive or negative infinity, the value converges to a single number. Diverges means it gets bigger, 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 or more negative and more negative, whichever the case may be. This diverges because this expression just keeps getting bigger and bigger and bigger as b gets bigger and bigger and bigger. So we're going to turn this into another limit problem. The limit as b approaches infinity of the integral from 0 to b of e to negative 2x dx. Now, we can find the antiderivative of e to the negative 2x as long as there's a negative 2 there. In order to do that, we need a negative 2, or a negative 1/2 right out there. So now we can find the antiderivative of that simply using the integral of e to the u is just e to the u times du. Or, sorry, the antiderivative of e to the u du is just e to the u. So we're going to have 1/2 e to the negative 2x as our antiderivative. We're going to evaluate that from 0 to b. I'm going to need a little more room. So if we do the upper bound of integration, it's going to be negative 1/2 times e to the negative 2b, and then we subtract at the lower bound. If we plug in a 0 for x, we're going to have e to the 0, which is 1, and then negative 1/2 times 1 is negative 1/2. So we need to figure out what the limit is as b approaches infinity of negative 1 over 2e to the 2b plus 1/2. Now, as we plug values in for b that are getting bigger and bigger and bigger, then the denominator itself is getting bigger and bigger and bigger, but the numerator stays negative 1. So we have a fraction where the denominator is getting bigger, but the numerator isn't. What that means is the fraction itself, the whole fraction, is getting smaller and smaller and smaller, converging towards 0. So this whole expression then becomes, as b gets sufficiently large, tending towards infinity, the expression becomes 0 plus 1/2. So the whole value of the expression is converging, or it converges to 1/2. Okay, number 21, we have same thing. We're going to evaluate this improper integral by evaluating a limit. So now, since the lower limit is negative infinity, I'm going to use a approaches negative infinity, and then the antiderivative, or the integral, becomes from a to negative 1, and I'm going to switch it to be x to the negative 5th. The antiderivative of x to the negative 5th, or x to the negative 5, is x to the negative 4 divided by negative 4. We're going to evaluate that antiderivative from a to negative 1. So the upper bound becomes negative 1 to the negative 4 over negative 4. And then we subtract at the lower bound a to the negative 4 over negative 4. Now, negative 1 to the negative 4 in the numerator, we don't like to have negative exponents, so I'm going to move that down to the denominator. So that becomes 1 over negative 4 times negative 1 to the positive 4 minus, same thing, we're going to do 1 over negative 4 times a to the positive 4. Now right here, negative 1 to the positive 4th, that's just 1. And 1 times negative 4 is negative 1/4, so we have negative 1/4 plus, because we have minus a negative right there, 1 over a to the 4th. Now, let me erase this equal sign. Because what we're doing now that we have this antiderivative, if you recall, we need to now evaluate the limit as a approaches negative infinity. So what we're doing is plugging in values there for a that are getting more and more negative. But what happens when you raise a negative base to a positive exponent is it comes out positive. So what's happening with this expression there, a to the negative, or a to the 4th, is it's getting larger and larger and larger, even though a is negative because the exponent is positive. So the denominator is growing without bound, the numerator stays fixed at 1. So as with this problem here, this part of the expression converges to 0. So the whole expression converges to negative 1/4. All right, the rest of these problems are just anti-differentiation or finding the antiderivative. And it's up to you to decide which technique to use. Is it going to be integration by substitution? And remember, substitution could be general power rule, it could be exponential rule, or the logarithm rule. Is it going to be integration by parts, or is it going to be integration using partial fractions? As a general rule of thumb, first one to try would be substitution rule, either by general power rule, exponential rule, or the logarithm rule. I think those are the most straightforward and the easiest. So that's going to be our default. For example, number 22, I notice we have e to a power, so we could try the exponential rule, which means that the power would be our u substitution, so u equals 3x to the 3rd minus 4. Du then becomes 9x squared dx. So we've got x squared dx, and mentioned a couple of times in class, if the variable and the exponent match, but the coefficient doesn't, that's fine. You can mess around with the coefficient to make it work. For example, 45 could be 9 times 5, and then we've got the 9x squared. So 5 times 9x squared e to the 3x cubed minus 4 can be rewritten as 5 times the antiderivative of e to the u du. And then the antiderivative of e to the u du is just e to the u. And then u was 3x cubed minus 4. Now notice we have similar thing there. We have e to a power, so we could try u substitution as we did with the last problem, which means u would be the exponent, 3x, and then d would be 3 dx. We've got the dx, but we have this x squared that's not accounted for in du. So u substitution isn't going to work on this. So the other option, if you have one expression being multiplied with another expression, oftentimes you can do integration by parts, which means we need to try to get a u and a dv. U needs to be an expression whose derivative is more simple, so I'm going to let u equal x squared because du is 2x. If you decrease by powers, this is a second degree polynomial, this is a first degree polynomial, that's considered becoming more simple. So du is more simple. Dv then would have to be the other factor of the product e to the 3x dx. Now we've got to find v. V is the antiderivative of dv, meaning it's the antiderivative of e to the 3x dx. Well, in order to find that, let me just write it this way. We need to find the antiderivative of e to the 3x. The only way we can do that is if we had a 3 here and then a 1/3 in front. Now let me explain that a little more in detail. If I want to find the antiderivative of e to the 3x, that means I need to do a mini u substitution here. U is equal to 3x, which means du is 3 dx. I've got the dx, but I'm missing the 3, so I need to multiply by a 3 there, and then divide or multiply by 1/3 out in front. And then 1/3 times the antiderivative of 3e to the 3x becomes 1/3 times the antiderivative of e to the u, and the antiderivative of e to the u is e to the u, and u is 3x. So there's your antiderivative, 1/3 e to the 3x. And now it's up to you to remember the integration by parts formula. It's u v minus the integral of v du. So u times v minus the integral of v, and since v has a coefficient, I'm going to write it out there, times du Now we need to find the antiderivative of this expression. So this is one of these 5% problems that you don't see very often, but it does happen every now and again. When you get to this point, you end up needing to do integration by parts again. And the reason that has to be is if we try to differentiate this, we could let u equal 3x, and then du would be 3 dx, and then we have this extra variable there that we can't account for. So we need to do another integration by parts, which means we need to choose another u and another dv. So I'm going to let u equal 2x and dv equal e to the 3x. So now du is is 2, and then v, we've already done this one, it's 1/3 e to the 3x. So writing this first part, we can just rewrite as x squared times 1/3 e to the 3x minus 1/3, and now this, the integral of e to the 3x times 2x dx, that's what we're going to expand using another integration by parts. So we need a u times v minus the integral of v times du. Now, we've got another coefficient here, 2, so I'm actually going to write that in front. Instead of multiplying by 1/3, I'm going to multiply by 2/3. This integral we've done several times. The integral of e to the 3x is 1/3 e to the 3x. So we've got x squared times 1/3 e to the 3x minus 1/3 times 2x times 1/3 e to the 3x minus 2/3. And then the antiderivative here, remember, is 1/3 e to the 3x. So simplifying this, x squared times 1/3 e to the 3x. If I want to distribute that 1/3 into the parenthesis there, whoop. And then we've got 2/3. Actually, let's try this. The 1/3 and the 2 and the 1/3 there are all going to multiply, so we're going to have 2/3 times 1/3, that's 2/9 x e to the 3x minus, now we've got that 2/3 makes 2/9 multiplied by this 1/3 is 2/27 e to the 3x plus c. Now, since this one is already in the form of a rational expression, we could try to get it into this form, because if you recall, that's just the natural log of u, so that's what we're going to try. So that means we're going to let u equal our denominator, and then du is its derivative. And this works out perfectly. 4x dx is du, so we can write this without manipulating anything as du over u. So this equals the natural log of u, which is the natural log of 2x squared minus 1. Actually, those need to be in absolute values. Now 25, it is in the form of a fraction, but the reason that we don't want to try to do du over u is because we have an inside function and an outside function. Oftentimes when we have an inside and an outside function, we can try to do u substitution with the general power rule. But first I'm going to rewrite this to have so that we don't have a rational expression. I don't like the fraction there. So I'm going to move this term up to the denominator, or sorry, up to the numerator. By giving it a negative exponent. So now we've got this inside expression there. I'm going to let that be u. So then du is 3x squared dx. So the x squared and the dx match. What doesn't match is the coefficient, but that's fine, because 6, I can change that into a 3 in front and a 2 outside. So now I've got my 3x squared dx, which can become du, and this can become u. So this becomes u to the negative 3 times du. And the antiderivative of u to the negative 3 is u to the negative 2 divided by negative 2 and then the 2's can cancel, leaving it negative u to the negative 2, which is negative 1 over u squared Okay, number 26, x squared times the natural log of x. Oftentimes when you have an expression that's a product meaning one factor multiplied by another factor, and one of the factors is the natural log of something, oftentimes that ends up being integration by parts. So we need to use a u and a dv. It wouldn't make sense to make dv the natural log of x because there is no antiderivative, or there's no simple antiderivative for that. So we're going to let u equal the natural log of x, which works out well because the derivative of natural log, remember, is 1 over x. And that's more simple. 1 over x is more simple than natural log of x, which means that dv is x squared. So when you take the antiderivative, you get x cubed over 3. So now we use the integration by parts formula, which is u times v minus the integral of v, and v is x cubed over 3, or 1/3 x cubed. So there's v times du so that's natural log of x. X cubed times 1 over x is x cubed over x, or x squared. And then the antiderivative of x squared is x cubed over 3. So we have natural log of x times x cubed over 3 minus x cubed over 9 plus c. I notice right off the bat on number 27 we have an inside function and an outside function, and like I said, often, not always, but often that's an indication of general power rule, so we're going to try that one. U equals the inside function. Du is simply the derivative, and so we've got the x squared dx, which is perfect. If we have exponents that match, we can work around getting coefficients that match. 30, for example, is 15 and 2. So we can make the u substitution now and call this u to the 5th power. And the antiderivative is u to the 6 over 6, which is u to the 6, because the 2 and the 3, or the 2 and the 6 cancel the 1/3. So this is the answer there. Now I notice on 28 that it's in the form of a rational expression, so we could try to do du over u like we did on the last page, which means u would be x squared plus 2x minus 3. Du would be 2x plus 2 dx. The problem is we're not going to be able to get 2x plus 2 and 7x plus 1 to match. So we're not going to be able to do du over u, so integration using the logarithm rule isn't going to work. There's no inside or outside expression, so we can't do general power rule. I can't really move the denominator up to the numerator to try to use integration by parts. So this is going to be an example of partial fraction decomposition. We're going to need to write this as a over something plus b over something. Now the denominator can factor into x plus 3, x minus 1, so the problems that we did before, we would multiply this whole expression by the lowest common denominator, which is x plus 3 times x minus 1. What happens there is then we would end up with 7x plus 1 equals a times x minus 1 plus b times x plus 3. Now we're solving for a and b, so we can let x equal whatever we want. So I'm going to let x equal 1, because if I plug that in there, I get 1 minus 1, which is 0. So a disappears, allowing me to solve for b. So when x equals 1 and I plug it in there, I get 7 plus 1, which is 8. When I plug it in there, I get 0 times a, which is 0. If I plug it in there, I get 1 plus 3, which is 4b. So b equals 2. Now I want to let x equal negative 3, because when I plug it in there, I get negative 3 plus 3, which is 0. It's going to let b disappear. So when I plug it in there, I get negative 21 plus 1. It's negative 20. Plug it in there, I get negative 3 minus 1. That's negative 4a. So a equals 5. So this is really the antiderivative of both of those separate partial fractions. So it's the antiderivative of 5 over x plus 3 dx plus the antiderivative of 2 over x minus 1 dx. And that 5 I can move in front as a coefficient. Same thing with that 2. And now we've got an example of du over u, which again is the natural log of u. So this is 5 times the natural log of x plus 3 plus 2 times the natural log of x minus 1 plus c. Okay, finally we've got last one here, the antiderivative of natural log of x. I've said it a couple times in this video that there is no antiderivative of natural log of x. There's no quick formula for it. We can find it, but this is going to be integration by parts. Natural log of x is one of the factors, and dx is the other factor. So that's going to be our u and our dv. U is going to be the natural log of x, and dv is going to be 1 dx. Derivative of natural log of x is 1 over x, and the antiderivative of 1 is x. So now we use integration by parts formula. U times v minus the integral of v times du. And then the x's here would cancel. So that's just the antiderivative of 1 dx. And the antiderivative of 1 dx is x. Now just let me make you aware of a few common mistakes I see here. First of all, these x's cannot multiply together to be x squared, because this x is inside of a natural log. These x's can't subtract from each other, because this x here is part of that factor, or sorry, is a factor of that product. So the more common way of writing this is to move that x in front and to write this as x times the natural log of x minus x plus c.